Rho Ratar. Buffon's needle problem. In this video, we're going to talk about an experiment associated to the scientific constant pi. The experiment will run through an MS Excel VBA-based visual illustration tool. For centuries, mathematicians, statisticians, and scientists have tried to understand the universe and its phenomena in terms of patterns hidden with it. One thing they have discovered from these patterns over the centuries is the presence of some constants associated to the nature. The amazing thing about these constants is their unique ability of engraving their footprints on many natural and universal phenomena. This allows scientists to create a model that rationalizes past experiences and predicts the future behaviors of a particular phenomenon. So, in this video we're going to talk about such a constant related to nature. We all know about this constant, and it's known as pi. And it will not only be just a talk about pi, but also you're going to know an experiment related to pi and how to conduct such an experiment using MS Excel VBA. Pi appears in many other phenomena. In particular, it appears in probability theory quite a bit. So, in this experiment also we're going to calculate the probability of an event, where the probability can be expressed in pi. The question associated to this experiment is known to be the Buffon's needle problem. First, let's understand the experiment and its events. Suppose you have a piece of paper and a needle. On the paper, let's get some parallel lines drawn. But the gap between each pair of lines should be equal to the length of the needle. Then we drop the needle onto the paper. There are two possible events that can happen here. One is needle cuts a line. The other is needle doesn't cut a line. Then it turns out the probability that the needle lands so it crosses a line is 2 over pi, or about 64%. This probability can be calculated using relative frequency approach in probability theory. In simple terms, what we do here, we repeat the experiment for many times and count the number of times that the needle crosses the line. Then to get the probability we divide the number of occurrences needle crossing a line by the total number of trials the experiment repeated. Higher the number of trials the experiment conducted, more the accuracy we reach for the probability. Hence, the name, the relative frequency approach in probability. Secondly, I'll show you the tool I created to demonstrate the experiment and then explain how it calculates the probability. This is the visual illustration tool which I created for the Buffon's needle problem. Our intention is to repeat the experiment hundreds or thousands of times in order to calculate the probability. Let's say we have run the experiment only once, then the probability will be the number of times the needle crossing the line divided by the total number of trials the experiment conducted. Thereby we get the probability only for the first sample. Let's call it P1. If we run the experiment for another sample, then we get another value as the probability. Let's call it P2. Likewise, this tool can run the experiment for any number of samples and calculate the pooled estimate over all the samples using the calculated probabilities at each sample. Here the pooled estimate is simply the average because the number of trials per sample is same for all the samples. This pooled estimate is more accurate than its for one sample. So here all we need to set these two values first. First value is trials per sample, by which we set the number of times we toss the needle per one sample. Let's set this to 100. The second value is samples per run, over which number of samples we run the experiment. Let's set this to 10. Then we run the experiment. You can see, the tool illustrates the needle's random tosses here and the calculations here. At the end of the experiment now you can see the pooled probability of crossing a line here. It's an estimated value for the intended probability. But here you can see the exact probability which was given by 2 over pi. Below those two I formulated the cell to calculate the error, the difference between the exact probability and the estimated probability. Using the estimated probability, we can invert the calculation to get an estimate for the pi, which is denoted here as the pi hat. This is the exact mathematical value for the pi. So here we get the error for the estimated pi. which is the difference between the exact pi and the estimated pi. So this is the experiment of Buffon's needle problem and how we experimentally show that the probability nearly approaches the proven value of 2 over pi. There is a link to the VBA code of this experiment in the description area below. If you want me to do another video explaining that code, please comment it with a hashtag. Once it reached 100 comments requesting the video, then I'll do another video to explain the code. And if there are any other suggestions, please comment that too. If you really have learnt something from this video, please raise your thumbs up. And please subscribe our channel and hit the notification bell to reach our latest videos about so many patterns surrounding you. Thanks for watching. See you again.